an associate professor in immunotoxicology at this Institute for Risk Assessment Sciences and Faculty of Veterinary Medicine, and full professor in innovative testing in life sciences and chemistry at Utrecht University of Applied Sciences, Utrecht. His research focuses on assessment of effects of substances on inflammatory and allergic responses. He has been involved in several projects focusing on immune effects of airborne pollutants and currently leading the European Commission Horizon Project POLYRISK, aiming to understanding human exposure and health hazards of micro and nanoplastic contaminants in our environment. I kindly request Dr. Raymond, please share your screen and you can lead the talk from here on.
Okay, can you see my presentation?
Yes, we can see your presentation, but not on the presentation mode, but it is fine.
I will try it again. Is it now in presenting mode?
No.
Okay, but you can see my slides moving also.
We cannot see the slides moving. I think you will have to...
Try it again. And now? You see them moving or not?
I see you're on slide 2, but I don't see movement of the slides.
Okay, I'll try it again. Sorry.
No problem.
We just checked it, right? Try it again. And now?
No, we cannot see the presentation mode, but I think if you escape the presentation mode and just remain on the PPT format, we could move the slides in that way.
I see my slides moving, but and if I do it like this?
Yes, this works.
But you don't see it in presenting mode. I do like
No,
this.
we don't see it in presenting mode, but I think we see the content.
All right, then do it like this. Sorry for this. That normally doesn't happen. But anyway, I'd like to introduce POLYRISK, which is one of the EU projects that has been started a few years ago and actually is ending in this period. And it's about risk assessment of micro and nanoplastics. And you see here all the partners that were involved. All over Europe, people were involved, institutes were involved, among others, Hubert Devlin, who will present later on, and Esther Lense, she will also present on the work we did in human studies. So you all have seen probably, now I have to continue. You have seen pictures like this, probably, where there's depicted here that microplastics are from different sources. We inhale a lot of these microplastics and also ingest it. These are the main routes of exposure. And maybe there's also some exposure via dermal route, but that's not really very prominent. And the effects, actually, we don't know yet, but we suspect, based on particle toxicity, that there will be effects on the immune system. There will be some oxidative stress in some cells. And maybe there's also, in the end, some effects on cancer development. We also don't know whether the plastics by itself are active or the additives that are responsible for effects, but probably there's a combination of effects. On top of that, we suspect that microplastics, as other particles, may act as vehicles of many other substances, for instance, microbial substances, but also environmental pollutants that are around. That would be the Trojan horse effect. Well, in POLYRISK, we aimed for different aspects to study risk assessment of micro and nanoplastics. On top of everything, we had to develop methods to characterize and detect microplastics, not only to characterize them and see how they, for instance, age in the environment, but also to analyze exposure. And that is needed if you want to do some risk assessment, and I will come back to that in a minute. We also focused a lot of work on hazard assessment, and of course that means hazard identification and hazard characterization, and aspects that we were interested in were all kinds of particle characteristics, think of size, shape, and surface chemistry, but also chemicals that were leaching out of the plastics could be of interest. And we also paid some attention on carrier hypothesis, looking at effects of microbial contaminants. A main aspect was our exposure scenarios that were focused indeed on exposure, and the focus of POLYRISK was mainly on inhalation. And the ones that will be presented today, the exposure scenarios are indoor soccer players exposed to rubber granulate MNPs, and urban and rural outdoor air ambient MNPs. A long title, but these were the titles of our scenarios. Here they are depicted in a way that you can see them. So this is the soccer scenario in Norway, and the traffic scenario that was performed in Utrecht. All this information had to come together in our risk assessment framework. And the risk assessment framework was designed primarily by BFR in Germany, and it was meant to be a modular risk assessment framework where you could move from one tier to the other and go deeper and deeper into the framework and into the risk assessment. So it starts off with determining whether we deal with polymers or whether we deal with MNPs of different sizes. Can they be inhaled or not? Can they reach the distal lung? Will they stay, or will they be transported back up to the oral cavity and then swallowed maybe? Of course, it's important to look at the morphology. If it's a fiber, we already have a IATA for fiber grouping that's available from earlier studies. But if it's not a fiber, we could go to a tier where it's about polysoluble, low toxicity polymers, which are probably our microplastics. And then case by case and with group strategies, we could assess certain effects. And the focus of our project was on immunotoxic effect. Of course, ILSI is mainly interested in oral route exposure, and that's also that is also something that could fit in this framework. If you, for instance, don't have inhalation exposure, you could still have oral exposure, and then we would have a different risk assessment framework. Currently, together with EFSA, we are working on an extension of this risk assessment framework to the oral route. Okay, this is what we had in plan, and we have this framework now, but the basis actually was also whether these microplastics were active at all on the immune system. And here you see what could happen in the lungs if particles end up deep in the lung. They may transfer across epithelial cells, but they initially may also come in contact with alveolar macrophages that become stressed or activated, and they may release all kinds of pro-inflammatory mediators that attract other inflammatory cells to the place of insult where they can raise an inflammation. Also, they could activate dendritic cells that may activate in the lymph node adaptive immune cells like T and B cells. These are more or less the process that can occur in the lungs. And you see already here in these pictures that it may occur. It's not maybe not very clear here, but you see some inflammatory cells, you see particles, you see macrophages that have taken up these particles. With this in mind, we sort of designed an AOP for immune-related outcomes, although we mainly stuck with the initial key events. So what we consider is that particles may be taken up by epithelial cells. They may cause epithelial or also alveolar macrophage stress that can cause release of pro-inflammatory mediators that can activate leukocytes or activate leukocytes. That is the effect via epithelial cells or via macrophages in the lung, but it can also happen that particles, in particular the smaller ones, can cross the epithelia and directly affect leukocytes. In the end, and that's something we didn't come close to, is that the adverse outcomes that we expect from immune activation or immune modulation is that we may have increased allergies or increased inflammatory diseases. And if particles would suppress leukocyte activation, that may lead to increased infections or increased tumors or decreased vaccination. But again, we focus mainly on these early key events because that is something we can measure in our in vitro assays. To jump to our conclusions, I present here an overview of findings that we have with different particles on THP1 macrophages and dendritic cells. So here you see the list of particles, including commercial polystyrene particles, but also in-house made different particles, PVCs, polypropylene, polyamide, and some controls. And we also had particles that came from BAM, a German institute, polypropylene, polyethylene PET, and we had some particles that we obtained from the RIVM. But the message is actually that most particles are not very active with regard to inflammation. Only the particles that we received from BAM were active in activation of the immune system. All the other particles mainly reduced the metabolic activity and the membrane integrity of macrophages. So they were actually quite cytotoxic, but only at a relatively high dose. So most particles were not very effective, but if they were, you could predominantly see decrease of macrophage function, or in some cases, increase of macrophage function. The ones that were increasing macrophage function, polypropylene and polyethylene, appear to be aged in a way or activated with some surface groups, oxidative surface group, that had the potential to activate macrophages. And altogether, we came up with a sort of tier testing approach that addresses all these key events that I mentioned. And this is actually an overview of what you could do with testing effects via the inhalation route. What you could do, of course, is look at phagocytosis, activation of macrophages, activation or disruption of epithelial or causing epithelial stress, etc., etc. If you would go for the oral route, you could also look at epithelial stress and maybe effects on or release of inflammatory mediators. The last key event would then be leukocyte recruitment or activation. There's a huge amount of test approaches that is available. So in a sense, you could, with these test approaches, you could easily test all these aspects of MNPs, keeping in mind that MNPs are not really easily dissolvable, or actually not dissolvable. They are, if you bring them in culture, they will be in suspension together with the cells, and that hampers a little bit the exposure to these cells. So there's some difficulty still, but in a sense, you could measure the hazard effects of MNPs. So in conclusion, we have seen and I didn't show that, but you have to trust me here that all MLPs that we have tested so far can be taken up by cells, in particular macrophages. We see effects on all kinds of cellular processes, but with normal non-surface activated MLPs, that will be at a relative high concentration of 10 to 100 microgram per ml. But if you alter the surface in inducing reactive oxygen groups on the surface or adding biologicals, which I also didn't show, but you have to trust me that if you add these extra groups or extra surface, extra pollutants, then you will have, or you will see an effect on pro-inflammatory mediators. This illustrates for us the importance of aging and weathering. So if you want to learn more about MLPs, you should not rely only on primary particles, but you should focus on weathered and aged particles. Altogether, I think we have come to a conclusion that we have a tiered approach method for MLPs, but we still have a lot to do. Test more particles, test what really is important on the particles to activate immune cells or to inhibit immune cells. Here I would like to show the group of POLYRISK that was involved in all the work we've done. Here you see Hubert and here you see Esther in the back. And all these were, of course, very important to come to all these conclusions. And with that, I'd like to conclude here and thank you for your attention. And I'm willing to answer every question. So I will stop sharing here. Let's see how I do that. Stop sharing.
Thank you very much, Dr. Peters. The screen has stopped sharing.
Okay, good.
Thank you. We are open to questions in the coming few minutes. If you would like to address a few questions, please feel free to unmute your mic and directly ask Dr. Peters. We do have a question on the chat.
Yes. One question is, were the MLPs produced on purpose? Yes. But the PP and PE were not made for oxidation by accident, by production of the particles at somehow, but I think it's due to solving in acetone that we had these reactive surface groups. And you have to keep in mind here that the chemists are not very well known on the biology. So what they did, actually, they tried to make them water soluble and treated them in a way that they were oxidized. So that was more or less by accident, but turned out to be very nice for us, for the biologists. And also the particles made by Momentum, the other project, were all projects that we worked together with. They were all made on purpose for this study.
Thank you, Dr. Peters. We have one more question from Maria Carmen. She says that the tested concentrations, are they really found in normal human conditions? Of course, everything is toxic, everything depending on the
No,
dose.
I think it's, but of course we are not sure, but these are really high concentration. And maybe, I don't know whether Esther will say something about it, but she has done some calculations on based on her studies, and I still think these are quite high concentrations. Although we are not sure what happens if you, for instance, have inhaled particles and they end up in the vicinity of macrophages. So locally, there might be high concentration, but if you would calculate it on the whole surface of the lung, these are really, really high concentration. So really hazard assessment.
Ixchel Gilbert asks, is it known that what are actual background levels in humans on average?
Yeah, I don't know whether Esther, you will say something about this, but no, I don't know.
Only on the traffic-related microplastics.
Yeah, so we have some background information, right? So it is very low in the environment. And if you compare it to exposure of other particles, like car exhaust particles, etc., so it's on the low side.
Thank you. Christina Naren asks, were you sure that the particles were responsible for the effects, or perhaps the oligomers released by the plastics were the main problem? Did you analyze them, and how?
No, we didn't analyze that specifically, but yeah, we don't know. We thought about it, but our chemists were quite sure if you produce them, there's and I'm not a chemist, so I just repeat what they mentioned. If you have polymers and you want to make you increase the amount of polymers and the size, they immediately form particles. So what they claim is that you never have single polymers that are in a stretch. They will always form these particles, and maybe they are very, very small, like in the nanometer sphere. But actually, we asked our chemists, can you give us polymers of the same and not particles? But that was not possible. So no, we didn't check for the polymer effect. We only checked for the particle effect, as far as we know.
Okay.
And also you have to keep in mind that it's very, very difficult to analyze particles in the scenarios, for instance, but let alone for the in vitro studies. The amounts are so low in the cells that it's hardly possible. Unless you have dyed them with a fluorescent dye, and then you see them, of course. But that's only with for now, it was only possible with polystyrene, since we could buy that.
Thank you, Dr. Peters. Okay, do we have more questions? We do have a follow-up here.
Yeah, I tried from the beginning. I tried everything. I don't know what happened. No, okay. I think we have all the questions, right?
We do have the last one from Maria Carmen. They're supposed to be inert. That is the concept of conventional plastics, not oligomers.
And they should not form oligomers. Oh, that's more confirmation. Yeah, I thought it was meant that maybe there were oligomers in the microplastics. And then it's not true. That's a discussion that's for chemists, I guess. The only thing I was interested, or that I thought the question was about that oligomers would be present in the particles and would have an effect on their own, like maybe the monomers. Okay.
Thank you very much, Dr. Peters. Thank you for your time and the presentation today.
Okay.
We will move on to the next presenter of the day, and that will be Dr. Hubert Dirven. Dr. Hubert Driven is Senior Toxicologist in the Department of Chemical Toxicology at the Norwegian Institute of Public Health. He is a European registered toxicologist and has worked as toxicologist in academia, in a research institute, and in pharmaceutical industry before joining NIPH. Hubert has a broad interest from biomonitoring to development of in vitro methods and next generation risk assessment. He is involved in several EU projects, including Exposum, POLYRISK, OnTox, and PARC. Currently, his research activities focus on the effects of chemicals on the immune system, on PFASs, and on micro and nanoplastics. He's leading a PARC project on exposure and effects of chemical leaching from plastics. He's a member of several committees regarding the hazard and risk assessment of human exposure to chemicals. Dr. Hubert, you are free to please share your screen and lead the conversation.
Thank you very much. Let's hope that I'm a little bit more successful.
Fingers crossed.
Fingers crossed, yes. Yeah, you see it in the right mode, I hope?
Yes, we do.
Okay, good. So this is one of the human studies in the POLYRISK project, which we call the football field study in Norway. Because in Norway, we like to play football, because the weather is quite cold. So we have a lot of these artificial turfs, artificial football fields made from plastics. And in Norway, they are often indoors because we have a lot of snow in the winter, and then it's easier to do it, to play football inside these big halls. So here we see on this picture, we see artificial football grass fields with rubber granulates, these small black things that you see on the left side. That's very common. We have a lot of these fields in Norway, at least more than 1,200 inside and indoors and outdoors. But because these rubber granulates, they are made from old rubber tires. They are recognized as a major source of micro and nanoplastics in the environment, and that's why the European Union are preventing that more of these rubber granulates are used in these artificial fields. So from 2031, there is a European ban on using these rubber granulates in these kinds of fields. So we are looking for alternatives, and one of the alternatives that is done in Norway is to use crushed olive stones as an infill in these artificial football fields, and that's on the right side of the figure. So we did a study inside a hall with a lot of air measurements instruments to take air samples, and also a lot of biological tissues were collected. So this was the design of the study. We had 36 to 40 players, males and females, 16 to 90 years old. They played a football match of 2 times 45 minutes in a hall with olive stones as infill. And after 14 days, we have the same participants playing a football match of 90 minutes in a hall with rubber granulates as infill. And then we took a lot of blood samplings before the match. We took this from the same participants, of course, blood samples 2 hours after the match, 18 hours after the match, and we also collected urine samples as a pooled sample. And then we did, in the air samples, we looked for the mass of rubber by pyrolysis GCMS, the colleagues at the Free University in Amsterdam. The mass of PM10 was measured by weighing the filters. I will present some data that was collected by an institute in Germany, BAUA, about particle size, number, and composition. And we also looked at volatile organic compounds in the air samples. So this is the work done by Maaike Stange and Dirk Broosel in BAUA Institute in Germany. So we collected aerosol samples on a filter, a special type of filter with a gold coating. They did scanning electron microscopy. They looked at 50 images, and they counted particles and also the size of the particles on 20 images. And in order to make sure that this was really plastics that we were studying, they had a specific system in which they transferred the coordinate of the particles on the filters, and then they looked with confocal microscopy with micro Raman to try to identify the nature of the particles. So this was quite a lot of work. One filter took initially 1 week to analyze, so this is not a high throughput screening assay, but it's very sensitive. And so we have filters, and then they can make an image, and they can do a Raman spectrum. And for example, they say this is an olive stone particle, this is black tire rubber. We have a lot of sand inside these holes because it's also part of the infill. So we measure a lot of quartz, micro nanoplastics. This particular particle was identified as a PET particle. And in the olive stone hole, they also find fungal spores as in the air samples. So this is a quite sensitive method to look at the particles and to try to identify what is present inside these holes. And this is quite a little bit a busy figure, but this is the rubber granule, the olive stone hole indoor, which is called hole 1 because all the samples were scored blindly. They didn't know if it was which hole it was, and then they found quite a lot of particles, 28 million per cubic meter. So that's quite a lot of particles inside the olive stone hole. They found quite a lot of olive stones in the olive stone particles inside the air samples. They also found some black tire rubber inside the air samples, and also some micro nanoplastics. But as indicated before by Raymond, the amount of micro and nanoplastics, and also if you consider these black tire rubbers as microplastics, we have a lot of particles inside these air samples, and it's less than 5% is micro and nanoplastics or black tire rubber. If you go to the other hole, there was much less particles present inside the rubber granulate hole compared to the olive stone hole. Luckily we didn't see any olive stones in the air samples. That's good news. But we found black tire rubber, which is then can be from the rubber granulate, but it can also be from the outside air, because we find black tire rubber in all the air samples, to be honest, inside and outside. And we found also micro and nanoplastics, but in the rubber granulate hole, the total amount of micro and nanoplastics was also less. Yeah, like indicated, unexpectedly, we saw also spores inside the olive stone hole, but we didn't see spores inside the rubber granulate hole. So this is what the chemical composition of the aerosols that we measured in the olive stone hole. It was black tire rubber, it was olive stone quartz, and also some micro nanoplastics, the different polyethylene, polystyrene, and PET, for example. But we find also, the spores and some other components. So it's quite a lot of particles that we see with a very big variety of the chemical composition. Inside the rubber granulate hole, it was the black tire rubber again, either coming from the rubber granulates that were used in the football fields, but it can also be from outside, from the outside air. Quartz, micro nanoplastics, which is then rubber, PVA, PC, and PET. And we have also quite another mixture of particles present inside these holes. And then we looked at the volatile organic compounds, because if you enter these holes, especially the holes with the rubber granulate, there is quite a distinctive smell inside these holes. So we thought we were going to measure quite a lot of VOCs. So we had a panel of 58 VOCs. We could only detect 15 out of the 58. And 6 of these 15 were detected above the LOD. So we measured, we expressed in this figure then the total VOCs of these six VOCs, but the levels were quite low, and strangely enough, we see more a little bit higher concentrations in the olive sand hole than in the rubber granulate. So the total level of VOCs was really low compared to what is considered as acceptable levels. So what we see is that we had a low concentration of airborne particles, but mainly a lot of background particles. More particles detected in the olive sand hole. MNPs and black tire particles were detected in both holes. We had spores only in the olive sand hole, and we had very low levels of volatile organic compounds in both holes. Then we were looking for chemicals in urine, so we asked all the participants to collect all the urine samples, and we made 2 pools from the morning of the match to the first visit at NIPH, and then we had another pool, first visit at NIPH to the next morning. And then we analyzed for polycyclic aromatic hydrocarbons, metabolites in the urine samples. We looked for bisphenols, phenols, for phthalate metabolites, and also DINCH metabolites, which is a phthalate substance. And then my colleague Berit Granem did quite a lot of quite complicated statistical analysis to look for if we have higher levels after the match compared to before the match, and then of course comparing the olive stones versus the rubber granulate. And also we looked at infill separately, the pool 1 versus pool 2. And these are quite data. We are still analyzing and trying to do even more statistics on all these data. But for example, 1-hydroxypyrene, which is a quite accepted marker for polycyclic aromatic hydrocarbon exposure, If you look at the olive stone and the olive stone before the match and after the match, the levels were the same, and also the levels in the rubber granulate hole are not really different before and after, and also not different from the olive stone hole. And we have done, we have other markers for other polycyclic aromatic hydrocarbons, and also for this is the sum of 4-hydroxyphene and terrain metabolites, and also we see the same picture. We don't see differences between the rubber granulate hole and the olive stone hole, and also not before and after the matches. And then we looked also for BPA and bisphenol S and some other bisphenols. And we also did it for a number of phthalates, different phthalates. But the conclusion is, this is comparing the rubber granulate compared to the olive stone hole. This is then the rubber granulate hole, and it's expressed in another way, more statistical correct, before the match and after the match. And we don't see differences between all these markers after the match, before the match. So the conclusion was that we don't see any statistically significant differences in metabolite levels in urine samples before and after the match, or between the holes and the compounds that we studied were the polycyclic aromatic hydrocarbons, the phenols, and the phthalates. Then the colleagues in Amsterdam, the group from Maria Lamoret, they did a lot of work on characterization and quantification of micro and nanoplastics in blood, based on a mass of polymers with pyrolysis GCMD multi-detecting. It was a method that was described already before, and it was further developed by a PhD student called Lorenzo Schibatti. We had micro nanoplastic exposure was quantified by measuring a number of polymers that are indicated on this slide. And also, since we had quite a lot of rubber from rubber tires, they also used two markers for both natural and synthetic rubber. Then it was a little bit disappointing that we had quite a lot of samples analyzed, 229 from both the holes and at 3 different time points. But we only saw in a limited number of samples, less than 6%, we found these polymers quantified then. And then, of course, you can also look at the level of detection and the level of quantification, and then we see a little bit higher detection rate. But most of the times, all the levels were below the level of detection in the majority of the samples. This is for the polymers, and then you can do the same for the rubber particles markers, and also there we see we don't see a lot of these rubber inside the blood samples of our players. So we concluded that the developed method is not sensitive enough for routine biomonitoring. And also, Esther will probably show this, there is a high intra-sample variability observed for both the polymers and these rubber particles in blood. And that is probably because you're really measuring particles. So it's a little bit by chance that you see that you take 1 milliliter of blood and that you see a particle. And if you take from the same blood tube, if you take another 1 milliliter, then you don't see it. So it's not really a reliable method for routine biomonitoring, the method that the colleagues in Amsterdam developed. We always believe that the immune cell system is very sensitive for effects of particles, and that's why we spent quite a lot of efforts in almost all studies to do quite intensive immune cell profiling, because we have now tools available in the labs to study the immune system. We have CyTOF or spectral flow, in which we can measure a lot of surface and intracellular markers on cells. And we can do all kinds of sensitive analysis method to analyze the data and to try to identify which of the cell populations are really affected. And we see in, for example, here we have using the site of machine that we have in our institute, we look for 42 surface and intracellular markers inside blood cells. And we see, for example, here the neutrophils. This is before. This is the olive stone hole. Then this is before the match. This is after the match, and this is then 18 hours after the match. So you see an increase in neutrophils, but then after 18 hours, it's going back to baseline levels. And for the rubber granulate hole, you see the same pattern for the neutrophils and as for the olive stone hole. This was at least a cell population that was really that we see differences at the different time points. The same was for another dendritic cell population that we saw immediately after the match a decrease in these cells, but also 18 hours after the match, the levels has returned to baseline levels. And this is for the olive stone hole, and this is for the rubber granulate hole. It's more or less the same pattern. So we see differences, but it's that we don't see differences between the olive stone hole and the rubber granulate hole. And then you can do this really with this clustering analysis. You can look at different populations, and then we see that if you do this, that we have a number of significant altered immune cell populations across sampling time points. You see that the most pronounced effects are after 18 hours, both in the olive stone hole and the rubber granulate hole. And this suggests that maybe we should have waited longer with taking the third time point. The 18-hour post-sampling time point might be too early to investigate really the effects on the immune cell profiling. But that's something we can take with us for next study. Then we also have another tool. We can not only look at a lot of immune cells, but we can also look for a lot of cytokines now with an Olink proteomics platform in which we can, in the assay that we have been using in our studies, we can measure up to 48 cytokines in plasma samples. And we detected all the cytokines in our samples. For technical reasons, we only analyzed for 45 because we didn't trust for 3 of the cytokines what the measurements. And we also looked at the 3 different time points before the match, 2 hours after the match, 18 hours after the match. But the differences were consistent between both holes. And so the findings that we see are more likely related to a general particle effect and or physical activity. We know that if that you have physical activity playing a football match, that has an effect on the immune system. So this gives just an indication about, well, at the different time points, the T2 is after the match and T3 is 18 hours after the match. Sometimes some of these cytokines goes up and some of these cytokines goes down. But most of the cytokines we see the same effects in both the olive stone hole and the rubber granulate hole. We have some markers that we only see differences in the olive stone hole, and also some markers that only have that we see differences in the rubber granulate hole. We are still analyzing the data because it's a lot of markers that we have measured in a lot of samples in different scenarios. So we are still analyzing, finding the most appropriate statistical analysis to look at the data. So this is the preliminary conclusions from our studies. But we conclude that the total rubber concentration is low in both holes, and that we have much more particles in the olive sand hole. That was unexpected, to be honest. And also it was unexpected that we measured spores only in the olive sand hole. We have low levels of volatile organic compounds in both holes, low levels of metabolites of polycyclic aromatic hydrocarbons, phthalates and bisphenols in urine samples. And also in the rubber granulate, we would have expected higher levels compared to the olive sand hole, but we didn't see it. MMP levels in blood. Unfortunately, we need further work on the measurements of the micro nanoplastics measurements in blood samples. So the method is not, we have issues with sensitivity and reproducibility. For the immune responses, we don't see consistent differences between the halls. Neutrophils and dendritic cells, we see differences, but it's in both halls, and also in the plasma cytokine levels, we don't see differences between the two halls studied. So conclusions, it's also preliminary. This might change. This morning we were looking again at some of the new statistical analysis, and yeah, we have some findings that we need to follow up. But in general, we don't see differences in levels of chemicals and immune responses between the olive stone hull and the rubber granulate hull. And if there are changes, then it's probably likely to physical activity and/or the general particle effects, because we have a lot of particles inside these halls. And we only studied, of course, short time exposure, only 90 minutes played our football players on these halls. But the good news is that playing football on a field with rubber granulates as infill has no biological significant acute health effects in healthy volunteers. And there is a lot of people worried about these rubber granulates in Norway, but also in other countries. So this is quite good news for from a public health standpoint, that we don't see any marked differences. Yeah, so this is these studies. We need a lot of people. Berit Graan and Monica Andreas, they were the PIs of this study, so they were really important. But we had a lot of other people involved from our institute, but also from our institute measuring MMPs in blood samples, in air samples, and in these chemicals in the VOCs. So thank to all these people for contributing. And POLYRISK, yeah, is a part of the CASP cluster in this Horizon 2020 project. So that was my presentation, and I'm happy to answer any questions if there are questions.
Thank you, Dr. Hubert. We do have questions already on the chat. It's from Gerdana Alexandrova. She asks, can the physical activity help in reducing the effect to the body? And did you take the urine or the blood samples from people not playing, just sitting?
Now, the easiest question first. No, we had only people playing actively in the halls, and we only took blood samples from these participants. But we know from other studies as well that if you have physical activity, that you have an impact on your immune system. So that's something that we didn't study in this study. We really thought, when we designed the study, we were interested and we were expecting that we had more micro and nanoplastics in the rubber granulate hall, and we were looking for a similar kind of hall with another infill than the rubber granulates, and that's why we ended up with the olive stone hall. But yeah, as indicated, we don't see big differences between the two halls. So yeah, that was the basic question. The study in itself was already complicated enough to perform. But the good thing is also that it was the same group of people that played football on the rubber granulate hall and in the olive stone hall, so that we don't have a lot of inter-individual differences in the markers that we measured.
Thank you, Dr. Hubert. Do we have more questions from the audience? Yes. Did you expect really to find microplastics at micron size in blood?
Microplastics, not, but nano-sized plastics, smaller than 1 micrometer. You know, we know from in vitro studies that they can pass microbiological membranes. So I expect that we have some nano-sized micro nanoplastics inside blood samples, but yeah, the method that we used is to measure the mass of polymers. So we cannot discriminate between micro and nanoplastics, but most likely it's the nanoplastics that we should be much more worried about. You know, they can be taken up in blood. And yeah, it's very likely that we have some of these nanoplastics in blood samples, but the method that we have used in this study is not sensitive enough to. It's a mass-based method, so we cannot say if we had nanoplastics inside our blood samples.
We have one more question. Is it possible to conclude that there is no impact from rubber granulates, given that the pyrolysis method is not sensitive enough?
Yeah, we have no exposure. We have not reliable data on internal exposure, the biological monitoring data on the micro and nanoplastic levels inside the blood. But we have it on the immune system, the immune data. We have used state-of-the-art methods to study the immune system, both with CyTOF and with this O-link, and we don't see big differences between the holes. So at this moment, we cannot say that we have a micro nanoplastics exposure that has an effect on the immune system. That is something we can say at this stage.
There are further comments by Christina Nerin that spectroscopic techniques usually employed for measuring and detecting MNPs give the same response to oligomers. LCMS HR is sensitive for oligomers. And Ixel Oswald asks, are there similar studies performed in other countries with higher levels of contamination, particle matter, for instance, that could maintain MNP?
Similar studies inside these settings in artificial football fields. To my understanding, this has been a topic which has been very hot and with a lot of questions from parents, players, and other people involved in playing on these artificial football fields. But it's a very limited number of studies that have studied this, and I don't think any of these studies has done it in the detail that we have been doing it, combining air samples, biological monitoring for chemicals and for micro nanoplastics. So no, I don't think that there are similar studies available.
But I see, Hubert, that it's also about other studies, and we did, of course, a textile study.
Yeah, if it's other scenarios, then we have other studies as well. We have the study, the traffic study, and the textile study. To be honest, we see a lot of particles, but we don't see a lot of micro nanoplastics exposure. That is that is in general thing. And if there is micro
textile study, you know that we don't see much in a textile study even.
No.
I mean, we also see mixed exposure. That's what we see also in the textile study.
Yeah. And we see a lot of rubber. We see a lot of rubber in all our samples analyzed by this Bauer Institute. We see a lot of small rubber particles, which I think then it means that it is a very common thing in the air that we breathe. And it doesn't matter if you take an air sample in Norway, which is quite relatively a clean country compared to the Netherlands or Romania. We see rubber particles everywhere.
Thank
you.
But
all the scenarios, Esther will say the next scenario, the traffic study. So please stay tuned.
Thank you, Dr. Hubert. This leads us to our last presenter of the day. Okay. It shuts off. It shut off by itself.
But we are still here.
Okay.
Yes.
My screen blacked out.
No, we are here. And we hear you and see you.
Oh, excellent then. Okay, I'm back. Well, so this leads us to the last presenter of the day, and that is Esther Lesson. She is a PhD candidate in toxicology and environmental health at the Institute of Risk Assessment Sciences, IRAS, part of Utrecht University, the Netherlands. Her research focuses on how environmental exposures impact human health, spanning topics such as barbecue smoke, air pollution, and more recently, microplastics, with a particular emphasis on traffic-related microplastics. Her current PhD is conducted within the framework of the EU research project POLYRISK. I give the floor to you, Esther. Please feel free to share your screen.
Thank you. Okay, can you see my screen at the moment?
Yes, we do. Thank you.
Perfect. Great. So, for some reason I can't see it. Yeah, okay, it's working. Thank you. So the reason that we focused on these traffic-related microplastics is because they are the major source of unintentionally released microplastics in outdoor air. So they are part of this complex mixture called tire and road wear particles, and they are released from the tires while driving due to abrasion processes, after which they get mixed together with other types of particles, such as road wear, brake wear, and also road dust resuspension. And so mass estimations of these tire and road wear particles in the air vary some orders of magnitude. So estimations vary between 0.5 up to 11% of the total PM10 fraction in air. And these variations are due to differences in the microenvironments that the particles were collected, but also due to changes in the variations in the measurement, the analytical detection limits. So no epidemiology relevant studies have been performed yet focusing on specifically these traffic-related microplastics. Multiple observational studies have been performed, but they focus on other types of microplastics. And they found that increased levels of these micro and nanoplastics, they found them across the human body, including, for example, blood, but also excised plaques. And these increased levels were associated with an increased risk of all-cause mortality, myocardial infarction, but also stroke. But as I mentioned, these studies did not focus on tire wear particles. They are generally at a high risk of co-exposure bias. They did not or minimally adjust for covariates, and they could also be of a risk of reverse causality bias. On the other hand, multiple experimental studies have been performed, and they found dose response effects between these tire wear particles and various immune toxicological effects, such as increased oxidative stress responses, increased inflammatory cytokines, but also macrophage activation. That is why we try to address these research gaps by focusing on immunological and respiratory health effects of exposure to traffic-related microplastics, and we focus on a healthy young adult group of volunteers. So what was the study design? We performed a semi-controlled study with repeated measurements design. So that meant that we, within small groups of volunteers, visited 3 different traffic sites, including a stop-and-go location. So this was marked by a high volume of traffic, which were braking, accelerating again, but also cornering. And we hypothesized that at this site, we would see increased levels of these traffic-related microplastics released from the tires. Then we also visited an urban park site. This is more an urban background location in the middle of the city center, and a highway location, which is more marked by continuous driving traffic. So all the volunteers visited these 3 traffic sites with at least a washout period of 2 weeks. They stayed for 4 hours at each site. And we also asked them to cycle for 20 minutes each hour, so 80 minutes in total, to increase the inhaled dose. Moreover, we stood downwind of the local traffic sites, so that's why you see 2 arrows for the traffic sites. And we also performed on-site air pollution monitoring of various real-world exposure levels. So we included quite a broad set of air pollutants. So first and foremost, we measured, of course, the mass of various rubber polymers. So a tire is actually made up of both synthetic and natural rubber. So we included 2 markers for synthetic rubber, 2 for natural rubber, 1 combination, actually, the sum of natural and synthetic rubber, and a benzothiazole marker. We collected these particles using a high volume sampler within the PM10 fraction, and it was analyzed by this group in Amsterdam that Hubert already talked about, and they used this method called double shot pyrolysis gas chromatography mass spectrometry. And additionally, we also measured trace metals and also polycyclic aromatic hydrocarbons using various mass spectrometry techniques. We also measured these more classical air pollutants such as PM10, mass absorbance, which is another marker for black carbon. Black carbon using microethanometer, and ultrafine particles. We did not have a on-site ozone or nitrogen dioxide monitor available, which is why we used our and site-matched values from the local monitoring network. And we also collected data from the meteorological data. So beside all these exposure measurements, we also collected various health measurements. So blood samples were collected at 3 different time points: immediately before all the volunteers went to the measurement sites, immediately after, and the following morning, so 70 hours post-exposure. And with these blood samples, we determined the total and differential white blood cell counts using an automated flow cytometer. And we isolated plasma to measure the cytokine levels using an O-link proteomics analysis. So we focused on 42 different cytokine and chemokine levels. Then additionally, at only 2 time points, so immediately before and immediately after, we determined the lung function using a handheld spirometer. And we asked them to fill in a short questionnaire asking about all these respiratory symptoms. And these included, for example, cough, wheezing, fatigue, headache, itchy or running nose, that sort of thing. So we were interested in the associations between all the air pollutants and the various health effects that we measured. So to do this, we had in total 6 different rubber markers plus all the co-pollutants, and we specifically focused on the associations between the exposure, the post-exposures versus the baseline. So what we did is we had immediately after, and we subtracted the baseline measurements from that, and separately we had an analysis for the following morning, which we also subtracted the baseline measurements. And we use linear mixed models to assess these associations, where we accounted for the repeated measurements, including a random factor for ID. Additionally, we adjusted for various covariates, including temperature, humidity, pollen counts, but also a time trend. So the study was actually performed over 2 separate years and also over various months. So to account for this, we included a time trend. And because we have quite a number of tests to perform, we also applied an FDR correction. Then for the sensitivity analysis, we included some incidental events, and we, sorry, just a moment. And we performed for all the co-pollutants, all the co-pollutants using 2 pollutant models. So as I mentioned, the study was performed over 2 separate years. We included 23 people in total, of which most of them are actually female. They had a mean age of 30 years, an average BMI. And this was actually the incidental events that I was talking about. So some of the people mentioned that they had some passive smoking the day before, they took some alternative medication, or had a cold the week before they participated with the visits to the measurement sites. So to summarize some of the atmospheric findings, here you can see box plots of 2 of the polymers that we measured. So on the top, you see the synthetic rubber marker, and on the bottom, the natural rubber marker. And they are actually split by, so above you have the sample measurements that we collected at the various sites. So in yellow, you have the urban park, in green, the highway, and in purple, the stop and go sites. Then the various lab lengths and the field lengths. So these are actually filters that went to the measurement sites, but were not connected to the pumps to adjust for potential contamination. And these were all below the analytical detection limits. Then for the samples, we indeed see, as we hypothesized, that at the stop and go location, we observed the highest concentrations of both synthetic and natural rubber. And these levels were between 3 and 5 times higher compared to the park site. Furthermore, here you can see the correlations between the individual air pollutants. So we found quite high correlations between all the different markers for rubber. So we have the 2 synthetic rubbers and 2 natural rubbers, the SAM and benzothiazole. And the correlations varied between 0.75 up to almost 1. We also found moderate to high correlations between, for example, the black carbon markers, but also breakaway-related trace elements such as iron, copper, chromium, and manganese. So these 2 figures, they show the associations between an interquartile range increase in each of the air pollutants and changes in the systemic monocytes. So on the left, you can see the associations immediately after exposure versus the baseline. And on the right, you can see the associations for the following morning versus the baseline. And overall, we observed positive associations immediately after exposure between the traffic-related micronanoplastics and the monocytes. And these were actually not only sustained, but also more pronounced for the following morning. We see slightly more pronounced effects for the synthetic rubber markers compared to the others. But as you can see, we also found positive associations for instance, the breakout-related trace elements, iron, chromium, copper, and manganese again. So you can see one other endpoint, which is the neutrophils in blood. And here we observed a slightly different pattern. So we found a more delayed effect. So for the following morning, we observed increased associations, although these were no longer significant after FDR correction, but a positive trend was nonetheless still noticeable. But again, here we also saw positive trends for the breakout-related trace elements and also black carbon. So this is what actually also observed for the total white blood cell count and also the granulocytes. So this is why we also performed these 2 polluted models. So on the top, you can see the monocytes, on the bottom, the neutrophils. And in black, actually, each time you can see the single pollutant estimates between the different rubber markers. And if you go from left to right, what we did is that we each time additionally adjusted for one of the other air pollutants. So the first one is adjusted for PM10, the second one for ultrafine particles, etc. And how you want to interpret this is that if you go from left to right, when we adjust for all the other air pollutants, the estimates were actually quite stable and robust. However, what you do see is when we adjust it for instance, black carbon, we see some widening of the confidence intervals, which is, might be a sign of multicollinearity due to the high correlation between black carbon and the rubber markers. So then we move on to the results with the O-link. So here you can see 2 heat maps displaying the changes in plasma cytokine and chemokine levels associated with the traffic-related microplastic concentrations on the x-axis. So you have synthetic, natural, and the SAM. And then in red, you see the positive association, so an increase in the cytokine levels immediately after on the left side compared to the baseline. And then on purple, you actually have a decreased association. So we found For immediately after versus the baseline, we found a positive trend of cytokines EGF, MMP1, and interleukin-7. Moreover, if we look for the following morning, we saw a more significant decrease in, for instance, IL-18, but also CXCL9. And then we additionally had these two pollutant models, which I won't show at the moment, but we found overall similar trends after adjusting one by one for all the other air pollutants. And lastly, we also performed similar models for the associations with either lung function and the various respiratory symptoms. Again, these were only collected immediately after exposure and compared them to the baseline. And overall, we did only find null associations, so none of the air pollutants were significantly associated with any changes. So to summarize, I can imagine it's quite a lot to digest, also after all the other presentations. So we found traffic-related micronanoplastics that were positively associated with total and differential white blood cell counts. We found an increase in the monocytes, mainly immediately after the exposure, and these were more pronounced the morning after. Then we found borderline significant associations with cytokines EGF, MMP1, and IL-7, and a significant decrease in CXCL9 and IL-8 the following morning. What we did not find were any associations with the more classic inflammatory cytokines and chemokines. This might suggest that we don't see a potential immune activation pathways beyond the more classical inflammatory phenotypes and pathways, but it's just unclear what this really means biologically speaking. However, it does give an interesting basis for future research. Moreover, as also Hubert indicated, we focused on short-term effects and on a very healthy young population, and it remains unclear whether we would find similar results with more vulnerable populations. And of course, I would like to highlight some strengths and limitations of our study. So as I mentioned multiple times, we did not include lung function measurements the following morning. We could not stratify for sex or ethnicity due to the small sample size. And we had some signs of multicollinearity issues, which might hamper the interpretation of the results. Then for the strengths, we had quite a robust study design. So we include these repeated measurements with pairwise differences, which means that we limit the influence of potential confounders. We have a relatively large exposure contrast. Because we focus on this within day, within person differences, we did not need absolute exposure levels. And with that, I would like to thank all the people that participated and helped with our study. Of course, the volunteers, but also the co-promoters, promoters, all the people that helped with the field work, the people who helped with the analysis from the University of Amsterdam, and from UC Utrecht, who helped with the analysis of the white blood cell counts, and INEA, who helped with the exposure measurements. And then if you have any questions, I'm willing to.
Thank you very much, Esther.
Yeah.
We open the questions right away. Please feel free to unmute yourself or write the questions on the chat as well.
Well, everything is clear.
Seems like it was very crystal clear, indeed. We give it one more minute, otherwise we could say thank yous. Christina says congratulations for the successful project. Thank you, Christina. So we don't have any more questions from the audience. Thank you very much for your attention today, and please feel free to join the community of practice of microplastics to be updated on upcoming webinars and the events and the workshop for microplastics in 2026. Thank you very much for your time, and hope to see you again in an upcoming webinar.
Okay, thank you.
Thank you to the speakers as well. Thank you for your
Bye-bye.
time.
Thank you.
Bye.
Bye-bye.
Thank you. Bye-bye.
Thank you.